Okay. If not, today I'm going to start on looking at another way of detecting exotic energy injection in the early universe. And this is using something that is, somewhat on the horizon, maybe, going to come online and become really important in the near future, which is 21 cm cosmology, which I think a number of you are actually working on, which is nice. And of course, there are a lot of lambda CDM stuff that you can do with 21 cm cosmology. You'll learn a lot about the cosmic dark ages, and then how the first stars turned on, and how reionization happened, and so on. And then after that, you can learn also about lambda CDM cosmology, because it gives you information about fluctuations during the cosmic dark ages as well. And so, on that front, you'll get a lot of information. I'm not going to talk about any of that because I'm honestly not an expert in that direction. So I'm only going to talk about BSM in this case. And the most interesting application, um, honestly, I think BSM in 21 cm cosmology is still underexplored, but the most obvious one that everybody kind of already knows it's really good for is looking for exotic sources of heating, which is, it turns out that 21 cm is a very powerful probe of that. Okay, so we've already discussed WIMP annihilation, also WIMP decay, and so we know that if you have, if you have processes like chi to E plus E minus, for example, or decays, which I haven't talked about, but today I'm going to focus on decays because decays is sort of the cleaner one that's easier to understand. And so for decays, you have things like, a dark matter particle going into 2 photons, for example, or dark matter going to E plus E minus, for example, and so on. Right? We know that all of these processes, and just in case it feels really weird to think of dark matter decaying because you expect dark matter to be stable. Well, I mean, you only need dark matter to be cosmologically stable, but it doesn't have to be exactly stable. And also in a lot of new physics models, that's true of dark matter. It's cosmologically stable only, but then it decays a very long decay lifetime and continuously injects these kinds of particles. But if you have these like EM interacting final states, again, EM interacting is important. Right? This gives ionization, which we've already discussed. But then also, of course, you would get heating, okay? And spectral distortions, as I mentioned. But the way that you should think about it is that ionization and heating really go together, right? Because if you're able to ionize hydrogen with some high energy particle, you're gonna kick out an electron. Unless the energy that you deposit is exactly 13.6 eV, that electron is going to have some excess energy, and that energy can, it's a charged particle, is moving through some very thin plasma that makes up the baryon, the baryonic intergalactic medium, and then that's going to find its way into increasing the temperature of the gas. Okay? So, as a quick benchmark to temperatures, let me discuss the conventional thermal evolution of baryons during the cosmic dark ages. Okay, so how do baryons, baryon temperature, how does baryon temperature TB evolve? Well, there are two effects. The first one is just expansion, right? Expansion of the universe. So there's adiabatic expansion. Okay, so that's number one, right? And you can go through, essentially how do you determine how the temperature evolves as a function of time? Well, you start from stress energy conservation. I mean, we know for photons that T goes as A inverse, but for non-relativistic fluids, The derivation is actually, I mean, I tried to look up, you know, examples of people deriving it, and there aren't that many that are very good. So I'll just show you how it works here. So it's just that rho b dot plus 3h rho b plus pb equals 0, which is just stress energy conservation. And then you put in, rho b, which is the energy density of baryons, is given by the mass of a baryon times the number density of baryons. Obviously, baryons are actually composed of, electrons, protons, helium, and so on. But you can imagine that actually I have to sum over all constituents in here. It's not really important. Plus this term, which comes from the ideal gas law, and the fact that the typical the average kinetic energy in an ideal gas is 3/2t, and then you multiply by the number density to get the rho b. Okay, and then of course the ideal gas law also says that the pressure for baryons is nBt. And if you plug all of this in, work it out, H is A dot over A. You get that Tb scales as A to the minus 2, or that dTb dt should be minus 2h Tb. All right. So this is just from adiabatic expansion. Okay. So T goes as A to the minus 2 for non-relativistic ideal gases, which are monatomic. Okay, which is true for baryons. All right. So that's one effect. The second effect, of course, is that we know from recombination that it's coupled to the CMB. And so at early times, especially when the baryons are completely ionized, they are fully coupled with the CMB, and so you should expect baryons and the CMB to share a common temperature, Tb, right? And the CMB can transfer energy into the baryons, and actually the baryons can also transfer energy into the CMB. Of course, it's mutual, and that just happens because of Compton scattering between the two fluids. So it's just gamma E to gamma E, right? So you can ask, okay, how does that change the temperature of the baryons? I'm not going to write down the full derivation of this term, but let's just look at it and see if it makes sense. So for this term, it would be dTb dt. Let me put adiabatic expansion here so that you know that it's just the adiabatic contribution, and then here is the Compton contribution. And it looks something like xe over 1 plus FHE plus xe, 8 over 3 sigma t rho gamma over me, T gamma minus T b. Okay? So that's the Compton heating term. It's heating if the photons are hotter than the baryons, of course, so it's a plus sign contribution to Tb. And let's just see that this makes sense, right? So first of all, obviously, if you're thinking about Compton scattering, the Compton scattering cross section is largest for electrons, and the neutral atoms don't do Compton scattering, right? So everything has to depend on the free electron fraction, which is the number of electrons divided by the total number of hydrogen atoms. So that's including both neutral and ionized. At least that's the convention that I use. And so this is the quantity Xe. Obviously, it depends on the Thomson cross-section, right? Because it is Thomson scattering. Sorry, I use Thomson and Compton like synonymously, but Thomson really is the low energy limit of the Compton scattering, and the energy transfer, you really only get energy transfer. Well, just remember that Compton just means this gamma E scattering at higher energies comparable to ME. All right. Then of course, the heating rate has to depend on the energy density of the photons. That kind of makes sense, right? If there's no energy density, then there's no heating effect. It depends on the temperature difference, T gamma minus TB. And again, this is easy to understand. If T gamma is equal to TB, then you expect no net exchange of energy, right? And so it must be proportional to the temperature difference. And then there's a divide by two things. This thing here is FHE is the number density of helium divided by the number density of hydrogen, which is roughly 0.08. That's what we derived when I was talking about BBN. And so this is like 1 plus 0.08 plus number of electrons divided by NH. And so this is like counting the number of degrees of freedom in your gas. And if you think about the reason why it's appearing here, it's because I'm taking some energy transfer and I want to convert into temperature. And so I have to divide by the number of degrees of freedom in my fluid. Okay, and so that's why there's something that looks like this here. And then finally, there's ME. And if you look at how Compton scattering works and how much energy gets transferred per scattering, you will find that everything is suppressed by 1 over ME. So if the electron mass is very, very large, then Compton scattering in the rest frame of the electron doesn't transfer any energy at all. Like the scattering is perfectly elastic. And the only reason why you can get energy transfer is because ME is finite, not infinite. Okay, so heuristically this makes sense. Okay? So you have these two contributions, and let's think about them. As I said, for this one, TB would scale as a to the minus 2. Right? For the Compton case, if Compton scattering is very effective, then if Compton is efficient, then TB would be equal to T gamma, right? Because this term here drives T baryon to T gamma, right? So you have very efficient Compton scattering. You will thermalize with the CMB. You will reach the same temperature as the CMB. And so when Compton is effective, TB should scale as a to the minus 1. Okay? So what's the picture here? Well, if I draw a plot, this is Z, this is TB, this is T. Let me draw T first. We know that the CMB is very simple. It scales as 1 over A. Right? And today, the temperature today is 2.7 Kelvin. Right? At very early times, the baryons are in thermal contact with the photons because of Compton scattering. And so the baryons track the CMB for a long time. So initially, TB is proportional to A inverse. And then, as the universe expands, rho gamma drops, and then X of E, right? Before recombination, X of E is 1, everything's fully ionized. After recombination, X of E drops to this residual value of 10 to the minus 4. And so that also takes a hit. And so at some point, Compton scattering becomes inefficient, and you transition to TB going as A to the minus 2. Okay? Until stars start to form. So I'll draw a line here and say, and let's just block it out. Okay, this is star formation. All right, once stars form, then it can emit UV radiation, ionization increases, and again, remember what I said about ionization and heating. If you're ionizing stuff, you're heating stuff, and so the temperature will start to go up. Okay, now let's find what this temperature is, let's call it T thermal decoupling between the baryons and the CMB. And as is always the case, what we'll do is compare this prefactor here with the other prefactor, which is this 2H. Okay, and if you write everything down and you make the approximation, well, okay, so let me just write down the T Compton side. It looks something like 8/3 xe sigma T rho gamma naught over me 1 plus ZTD to the 4. I'm sorry, I meant the redshift of decoupling, ZTD. And so rho gamma scales as 1 plus Z to the 4, and so at this point, wherever the decoupling occurs, the energy density is just rho today times 1 plus ZTD to the 4. And then this should be comparable to Hubble at ZTD, which is, if it's during matter domination, then it's, roughly something like this. Okay, you can solve this. You know what XE is. XE is roughly, you can just plug in roughly 10 to the minus 4. You know the Thomson cross-section. You know this because this is just pi square over 15 times T gamma naught to the 4 as well. And we know T gamma naught, which is 2.7 Kelvin. H naught, square root of omega m, You put everything together, you solve for ZTD. This is ZTD. And you find that ZTD is actually roughly 180. Okay? So it's surprisingly small. Even though recombination happened here, right? So Z recombination is equal to 1100, right? This is the point where a photon never encounters, well, up to a 5% effect due to reionization, never encounters an electron again. But this point is actually different. It's the point where the baryons don't get enough heating from the CMB to keep it in thermal equilibrium. And this happens at a much lower redshift. Okay? And so it happens at something like 180 or so. All right? So if you think about redshift evolution of T baryons, very simple. Initially A inverse, later on A to the minus 2. And then you can ask, what is the temperature of baryons at, let's say, Z of 20? I just picked 20 because we think that the cosmic dark ages is going to start ending at Z of 20. So once you drop below Z of 20, you start forming baryonic structures, and you start expecting the baryon temperature to go up again. Well, what is this? Well, this is roughly the temperature here, right? Which is just the photon temperature today times 1 plus ZTD. And then applying an A to the minus 2 redshift, which is just 20 squared over 1 plus ZTD squared. Okay? You plug everything in, this ends up becoming 6 kelvins. Okay? Or 10 to the minus 3 eV per baryon. All right? It's not super cold. Yeah. This one? Yeah, so the T gamma naught 1 plus ZTD is this temperature. And then this is at 180. Now to get the temperature at 20, I rescale by 8 to the minus 2. And so it's just this. Okay? Good? Okay. It's not super cold. It's not like cryogenics cold, but it's pretty cold. 10 to the minus 3 eV per baryon. And so again, the name of the game is, for exotic energy injection, if between T decoupling and Z of 20, which is, a delta Z of about 150, 160, right? If you can inject enough energy such that let's say you make an order 1 correction to the T baryons, then if you could measure the temperature, you would expect to be able to be sensitive to such sources of exotic heating, okay? So if we could measure TB at Z of 20, then any exotic sources of heating which contributes more, roughly more than 10 to the minus 3 eV per baryon could be detectable. All right. Any questions about this setup so far? Yes. Yeah, good. So that's a good question. The question was, is it possible that you dump so much energy that you mess with reionization in a way that you can tell, right? Yeah, very good. The answer is probably not. Yeah. So um, you can imagine. Okay, so let me go through the history of this. I think maybe around when WMAP was releasing its results, they were reporting very early reionization. So tau optical depth was quite big, I think, which corresponds to early reionization. And so people were trying to see if, let's say, something like dark matter annihilation or dark matter decay could actually fully reionize the universe. So even without stars, like it was more, like the dark matter contribution could have been more important than stars. And so people were very excited about that for a while because the optical depth that WMAP was getting, I think, was pretty surprising. Um, then, but the thing is that if you look at other constraints on things like dark matter annihilation or dark matter decay, so for example, let's say you wanted to reionize the universe with dark matter annihilation. Well, as I said, the increased ionization also affects the CMB anisotropies, and so there's a limit that comes directly from the CMB anisotropies as well. And if you try to take into account all of those limits, not just CMB, but also indirect detection from like gamma ray telescopes and so on, you find that it's very hard to arrange it such that at least dark matter annihilation and decay could like fully ionize the universe. But I think like 10% effects are actually still possible. Yeah. Any other questions? Okay, I want to go into a little bit of detail as to how we do the exotic heating calculation. So as you've seen here, there's one term that's from the adiabatic cooling. There's one term that comes from Compton heating, and now we wanna model exotic heating, right? And so we need another term that is TBDT exotic, right? So let's just call it TBXO. And now how do we do this? Well, the thing that we always try to compute is the energy injected, sorry, not the energy injected, but the energy deposited per volume per time. So this is how much energy is actually getting dumped into the intergalactic medium, the IGM, and heating the IGM directly. So this is a function of Z. So this is something that we have to compute based on our exotic heating model. And then, we have to do the same thing again, like this is an energy, so we have to convert to temperature. And so that just means that I need to divide by the number of baryons, I need to divide by the number of baryons, which is NH times this funny factor here. So again, it's like the number of degrees of freedom per unit volume. And then there's a factor of 2/3 that comes from the fact that the average kinetic energy of monatomic particles in an ideal gas is 3/2 times T. And so there's a 2/3 here. Okay? Simple enough. I just need to compute this. But if you think about what do you actually know, well, like what do you know most immediately? Well, you actually know straightforwardly the energy injected. Okay, and if you think back to our lectures on dark matter annihilation, we wrote down some equation that looks like rho squared sigma v over m chi for annihilation. But then, like I said, I'm going to focus also on decays in this lecture. And if you think about how decay works, if your decay lifetime is very long, then the fraction of dark matter that decays in some time t is just roughly given by t over the lifetime. Okay? And so the rate at which energy per unit volume is deposited is just the energy density of dark matter divided by the lifetime. Okay? So how do you think about this? Like in some small amount of time t, I would just multiply this by t to get the energy injected per unit volume. And the energy injected per unit volume is just the dark matter energy density times t over tau, which is the ratio of the time elapsed divided by the lifetime. Okay? Yes? No, yeah, annihilation, decay. This one? Good, yeah, all that would be in here. Yeah, you would just dump everything in here. Yeah. Yeah. Okay, so this is energy injected. It's not the same as energy deposited. Why? Because let's say you inject, let me give you a concrete example. Let's say you inject MEV photons. It turns out that MEV photons can't really do much. It's not a good, it doesn't really ionize stuff. It's not high energy enough to pair produce. And so if you have MEV photons produced somewhere in the universe, it free streams and the mean free path is actually much longer than the Hubble horizon. And so in some cases, you can inject energy and then it just free streams. It doesn't actually do anything. And then it has to redshift after some time. And then it finally is able to deposit itself at some later time. Okay? That's one thing. The other thing is that, like I said, you inject this amount of energy, rho chi over tau, that's like all of the energy injected. But then not all of it has to go into heating, right? Some of it can go into ionization, some of it can free stream, some of it can ultimately end up in spectral distortions, so on and so forth. Okay, so it's very complicated. There are many things that you have to take into account. But people have done the work of compressing all of that information down for you into just one number, and that's what we define as f of z. And so you can always compress everything down so that you can write this. And so all of your unknowns get compressed into this thing. Contains all complications. Okay, there are tools out there for you to compute what this is, including a code called Dark History, which I wrote a few years ago. For the case of applying, trying to figure out what the signal is in the CMB, these f of z's are already tabulated in codes like class. I'm not sure if it's in class or exoclass, but in one of those, you can just use those tables. Okay, yeah. Yeah, so in general, like one of the complications is that F heat depends on Z, the redshift, and then it also depends on the ionization level at that redshift. And so if you're sensitive to the ionization level, then you need codes like dark history. But if you're not, which usually is the case for CMB limits, then you're fine just using the tables. Yeah. Sorry, say it again? For CMB, it usually doesn't depend on XE. So for example, if you do like annihilation limits, the main redshift of sensitivity is like redshift of 600. And you can't really change that ionization level by that much. And so for CMB, it's usually fine just to take the tables in class. For decays, I think it's also fine. But then if you're thinking about like how much heating is there at like Z of 20, then it's really important to include the X of E effect. These are details that I'm kind of sweeping under the rug, but whatever it is, the only thing that you need is this F of Z, and there are tools to compute it, is the take-home message. Okay? So the full temperature evolution equation is just minus 2h Tb plus x of e over 1 plus f he plus x of e. And then there are two terms, which is this 8 over 3 sigma t rho gamma over me, t gamma minus tb. And then there is plus 2 over 3 nh dE f heat of z times dE injected dV dt. Okay? So you integrate this equation and you're done. You need one more equation, which is dx e dt, which is another thing. But you can imagine it's really the same situation here, which is that there are a bunch of terms that come that tell you how recombination proceeds, and these are very identical to the terms that you solve in order to determine how recombination proceeds in the CMB. Although usually for exotic energy injection, we use a simplified version of the one that's actually used in CMB analyses. Okay, so that's just some detail. And then there's also another term that is F ionization of Z. Some prefactor injected dV dt. Okay, and then you solve these two equations, coupled differential equations. Okay, so conceptually it's pretty straightforward. Any questions about this? Yeah. Very good. Very good. Um, Honestly, the answer is that it's probably not been thought through very well at this point. Fluctuations in the CMB are on the order of 1 in 10 to the 5, which is small. And so you have local fluctuations in the in let's say for annihilation, you have local fluctuations that are on the order of 10 to minus 10 for rho squared. Well, no, sorry, that's completely not true. Sorry, it's 10 to minus 5 for rho squared. And so you might think that that's a small effect, but honestly, I don't know. I don't know if anyone has thought through this very clearly. This always comes up, but nobody has really thought through this carefully. Another thing that people have thought of is it's like CMB secondaries as well. So things like you have annihilation happening in clusters, and then that kind of increases the electron number density locally, and so you should see like additional scattering through those clusters, and that's been interesting, but again, it seems like it's not important. Yeah, 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 yes, very good. In that case, it's really important, and that has been studied. Yeah, but it's only been studied very recently. Yeah. Yes. Yeah. I'll actually discuss that. Yeah, at the end of the lecture. Yeah. But for CMB, I still feel like I would like to look at it again and just make sure that everything is very small. I don't know if Julien has thought about this. Yeah, I don't know. Oh, is it important to think about dark matter annihilations and the fluctuations in density in the CMB? Yeah. Yeah, it's an interesting question. I'm not sure. Yeah. Yeah. Yes. So I mean, if you have thermal contact, like scattering, for example, between chi and baryons, then you need to solve also for the chi temperature. Yeah. For annihilation, it's just there's no like the two fluids aren't actually talking. It's just that yeah, it's just one way. Yeah. Yeah. Okay. So for completeness, because I'm talking about heating, and then I'm also talking about decays. I'm just going to go through the same calculation that we did for dark matter annihilation and ionization to kind of convince you that it is also worth looking at heating. And so we said that, so how much, well, okay. What lifetimes tau are we sensitive to? Okay, so we know that d energy injection dv dt, like I said, is rho chi over tau. Let's assume that, for simplicity, anything that's injected gets instantaneously deposited all into heating. In that case, we can say energy per baryon, energy deposited per baryon is dE dt is equal to 1 over NB dE dV dt. And that turns out to be 5 times mass of the proton divided by tau, where I've used the fact that omega b is roughly 5. Okay? So one thing you immediately see is that for decays, everything is always mass independent, up to this f of z, which is not mass independent. Okay, but that introduces a small mass dependence. All right, and then in order to find the total energy injected, I do the same thing. I do E, and then I integrate from the time of thermal decoupling, which is at 180, all the way down to 20, which is when roughly reionization starts. Okay, so that is kind of, if you inject energy above 180, it's very hard to heat the baryons because it's coupled to this gigantic reservoir with like 10 to the 10 degrees of freedom for every baryon. So if you dump a little bit of energy into baryons, most of it just gets shared with the CMB, and so it's very hard to heat baryons at this time. And so we really want to integrate only up to about 180, let's say, and stop at 20, because below that we'll probably be, we'll have to think very hard about reionization. Okay, and so I just have to do the integral over time, which in terms of redshift is just this, times 5 mp over tau. Okay, and then if you assume matter domination, you can do this integral. It's not difficult at all. And you will get E is equal to 6 Kelvin. And I chose 6 Kelvin because previously I said that at Z of 20, it hits 6 Kelvin. Well, I drew this in a completely crappy way, but I did say it was 6 Kelvin at Z of 20. And so the energy deposited per baryon is 6 kelvins times 1 over tau, and you would get 6 kelvins if tau is 5 times 10 to the 28, which is based on our current limits on dark matter decay, it's like 2 orders of magnitude stronger. Okay, so if we can achieve 21 cm cosmology in some way or form, and actually get a measurement of the 21 cm signal, then we would be able to be sensitive to dark matter decays at 2 orders of magnitude stronger than we are in some cases. Okay, any questions? All right, if not, then what I'm going to do is I'm going to tell you how we could do this measurement, how we could be sensitive to baryon temperatures at roughly Z of 20 or so. And that's through a technique that everyone is trying to make work in 21 cm cosmology. Okay? Okay, so what is it? Well, the idea is that every hydrogen atom has, obviously it has the usual, n equals 1, n equals 2 atomic levels. That's at the EV scale. But then there are also very small effects. So there are also things like couplings between the spin and the angular momentum, the spin of the proton and the angular momentum of the electrons and things like that. So if we include the spin-spin coupling, so spin of E coupling with spin of P, there is a small correction to the ground state where, if the two spins add up to a total angular momentum of 0 versus a total angular momentum of 1, there is a slight difference in the energy. And so the ground state gets split into 2. And the ground state here looks like 1 over square root 2, like up, down, minus, down, up. And then here there's like a triplet of states. There are 3 states, which is up, up, down, down, and 1 over square root 2, up, down, plus down, up. And these are s equals 1 states, and this is a single s equals 0 state. Okay, so it splits into a singlet, what we call a singlet, and a triplet. And the gap between the 2 states is has a wavelength of 21 cm, or in terms of energy, it's 5.9 micro EV. Okay, so it's a two-level system, and if you excite the atom into the triplet state, then it can decay into the singlet state and it will emit a 21 cm photon. Or if you shine a 21 cm photon onto this atom, it can absorb the 21 cm photon and transition from the singlet to the triplet. Okay, so this gives you some line in the spectrum. Okay, so that's the atomic physics underlying this. And now the right way to think about it is that all the hydrogen atoms out there, all the neutral hydrogen atoms, because you need an electron to couple to the proton, all of them in the gas are kind of like two-level systems. Okay, and you should think of the entire neutral hydrogen gas as a system, a thermodynamic system with these two states. Okay, so that's the right way to think about it, and it has a characteristic temperature associated with it. So you have some bath, well, sorry, some system of hydrogen atoms with two levels, with some splitting, given by, let's call it E21. And the number density of atoms in the excited state divided by number density of atoms in the ground state is just going to be given by 3 times e to the minus E21 over some temperature that we call Ts, which we call the spin temperature. Okay, so where does this come from? Well, e to the minus e over t is the usual Boltzmann factor, right? If you have a higher energy state with a mass splitting given by E21, then if you're in thermal equilibrium, well, for a two-level system, it really doesn't matter, right? The number density of particles in the excited state versus the ground state can always be described by some Boltzmann factor with some effective temperature called Ts that we call the spin temperature. Okay, and then there's a factor of 3 here, which takes into account the fact that the excited state is a triplet state, and so there are 3 degenerate states that it can go into. Okay, and now you should think of this system, thermodynamic system, and that it is coupled to a bunch of other things cosmologically. All right. Now the most obvious thing that it is coupled to is the CMB. Right. So there's the CMB over here, which has temperature T gamma. And these two things kind of talk to each other. Okay, so they're in thermal contact. So if you think about it this way, if you kind of dump the neutral hydrogen atoms and you have the CMB kind of streaming through it with a temperature T gamma, if you give it enough time, eventually the two systems will equilibrate with each other, and then you would expect Ts to go to T gamma. Okay? So that's how you should be thinking about it. And the spin temperature is the thing that sets the ratio here. And so what is the signal that we expect to get? Like what are we actually looking for? Well, again, the cartoon picture that you should have in mind is that this 21 cm line is very narrow. So at every redshift, let's say at some redshift z, and you have CMB photons coming in, okay? At every redshift z, you have some 21 cm photons in the CMB. Okay? So one thing that that is sometimes very confusing is that if you ask, what is the typical wavelength of the CMB, Um, it's more like, let's see, it's more like 3 cm. So like the central, so at z of 0, which is today, the peak of the CMB is at roughly 60 gigahertz, and this thing is at roughly 1.42 gigahertz. Okay, so you like when you think about the CMB spectrum, let me draw the CMB spectrum here. This is 60 gigahertz. You're talking about photons that are like here. Okay, so you're well into the what they call the Rayleigh-Jean's tail of the distribution. So you're using this end of the spectrum here, and then at higher redshifts, right? At higher redshift, let's say at redshift of 20, this 60 gigahertz is actually at 1.2 terahertz. But you're still using the 21 cm contribution. So as you go to higher and higher redshifts, you're actually looking at like further and further down into the tail. And you're relying on those photons to act as a backlight of gas at some z. Okay, so let me rewrite this in a way that actually is a little bit more obvious. So really, these photons are at 21 cm times 1 plus z today. And then they're coming into this slice of gas at redshift z. They enter the line, right? They hit the resonance between the transition, and then they come out very rapidly. Okay, it's very narrow, so that transition is very fast. And then at the end of it, you end up with some final number of photons. Okay? Now, the thing that you want to know is the change in the intensity, right? So before at high redshifts, well, sorry, before absorption, before entering the gas, entering the resonance, the intensity is given by the black body intensity at 21 cm. And this turns out to be given approximately by E21 squared over 2 pi squared T gamma of Z. Okay? And then you want to know what happened in this slice and what came out. So here the intensity is I21 BB at Z. And here the intensity is I21 of Z. Okay, and the way that we write it, we say that we define I21 of Z to be roughly given by E21 squared over 2 pi squared of T gamma of Z plus 1 plus Z TB of Z. Okay, and we call this number here the 21 cm brightness temperature. Okay, and this is the observable that we want to measure. Yeah. No, I'm sorry. Oh gosh. Yeah, this always happens, and I tell myself not to make this mistake, but unfortunately, I usually write TB in the context of energy injection. We're not talking about 21 cm. But now when I switch to 21 cm, people reserve TB for spin temperature. And then the gas temperature is usually written as TK. I'm so sorry. I just realized that I made the mistake that I didn't want to make. But now TB here is the 21 cm brightness temperature, B for brightness, and that's different from the baryon temperature. Okay? And that's going to be very important, and we'll come back to this. All right? Sorry about that. But let me reiterate again. You have some 21 cm photons coming in from the black body. Something happens. out comes the CMB photons at some different intensity, I21, and there's a difference between I21BB and I21, which is this, and then this is the difference. Okay? And then I divide by 1 plus z to redshift that difference back down to z of 0, and I define that to be the brightness temperature. Okay? So what are you actually looking at? If there were no gas, it would just be the black body. It would just be the black body, right? There would be nothing here. There would be no absorption, no emission, no nothing. And so if there was no change due to the presence of this gas, you would just see the black body, and that's not very interesting, okay? But this thing is actually making some net change to the CMB, and really what you're looking at is spectral distortions to the CMB at less than 1 gigahertz. Okay, so that's the right way to think about it, I feel, which is that when people say spectral distortions of CMB, they're always thinking about the distortions near the peak. But 21cm is really just looking at spectral distortions at the very low tail of the CMB and trying to see if there's any change to the CMB because of the presence of neutral hydrogen gas. Okay? Any questions about the setup? Okay. Good. So what can happen when you enter the gas? The gas, like I said, is a two-level system, right? And it really does exactly the same thing as what happens with lasers, okay, which is also a two-level system. And so there are three processes that can happen. Other than free streaming, of course, the photons can just free stream through the gas and nothing actually ever happens. One is spontaneous emission. Where you have one going to 0 spontaneously. So the excited state down to the ground state, the atom just decays. 2 is absorption. So this goes from 0 to 1. And then 3 is the important process that I guess Einstein realized was needed to understand such systems, which is spontaneous, stimulated emission, which is 1 goes to 0. But this is really, just the fact that the emission rate isn't just dependent on the number density of particles in the excited state, but also you can actually enhance the emission rate due to a Bose enhancement from photons. Okay, so if you have some population of photons that are at the 21cm wavelength already, then you enhance the probability of emission by some amount proportional to the number density of photons. Okay, and so this combination is essentially how lasers work, right? You don't just get spontaneous emission of the photon in a laser, but you also keep the photons that you produce in the cavity so that you continuously stimulate further emission in the laser. Okay, so you have these three processes, and how important each of these will determine what I21 is after the black body passes through the gas. Okay? So let me just derive what TB is heuristically. It's quite a rigorous definition, but there's quite a rigorous derivation. But I do skip some important details, and I try to motivate why these things are correct. But the first thing to do is to consider just 2 and 3 first. Okay, if we consider just 2 and 3 first, then what you realize, of course, is that everything must be proportional to the incoming, what did I call it? I21 BB. Right? What do I want to say? What I want to say is that sorry, let me say that again. What I want to say is that the absorption, the net absorption due to processes 2 and 3, right, which is I21 BB minus I21. So that's the change in the intensity. For processes 2 and 3, these must be proportional to the number of photons that you actually put in, right? Because absorption of CMB, how many CMB photons do you absorb? Well, the more CMB photons I put in to this part of the gas, the more photons get absorbed, right? So if I put in a ton of CMB photons for the same number of hydrogen atoms in here, I would absorb more. And then stimulated emission, of course, is a Bose enhancement from the background. And so the bigger the background, the more stimulated emission you get. Okay? And so, because of this rough heuristic, I should be able to write that 1 plus ZTB, which if you look there is proportional to the change in the intensity, is going to be given by something that's proportional to I21 black body itself, which is just T gamma. Okay? And there's a minus sign. And there's a term that looks like 1 minus e to the minus of some optical depth tau, plus another term that comes from spontaneous emission. Okay, so what did I just write down here? Well, first of all, like I said, I expect processes 2 and 3 to be proportional to the intensity of the black body you put in, which is proportional to T gamma. And then at the same time, the change in the intensity is given by some optical depth. And this optical depth just tells you how efficiently are photons absorbed in this layer. Okay, and so if tau is 0, then even though I pump in a huge amount of photons, none of them get absorbed because the two-level system is not the reaction, the rate of reaction is just not large enough for there to be any change before the photon redshifts out. But then at the same time, if tau is very, very large, then essentially all of the photons get absorbed. And so you get a huge deficit that is given by minus T gamma. Okay? Then, like I said, that was only for process 2 and 3, so that's 2 and 3 in this term. And then for process 1, which is spontaneous emission, I still need to add another term. Okay? Now, so there are two things that I'm still left as unknowns. One is what is this tau, and the other is what is this S of Z. Okay? So let me do the optical depth first. So again, you can derive it, rigorously, and there are many 21 cm reviews that do this. But let me just write down the final answer and tell you why it makes sense. So the optical depth is given by 3 pi squared A21 NH1 of z divided by 4 Hubble E21 square spin temperature. Okay, there are a few assumptions that I'm making, and just for the experts, I'll just say that I'm assuming that E21 is much less than Ts, and that there are no peculiar velocities in the gas, or rather, peculiar velocities unimportant. Okay, A21, this thing here, is the decay width. So it just tells you like what range of photons. So it doesn't only absorb exactly at 21 cm, there's a slight width to the absorption. And so A21 tells you what that width is. And also it determines the decay lifetime. 1 over A21 determines the decay lifetime. And so let's kind of look at this structure again. Does this make sense? Well, first of all, it's proportional to NH1, which is the number density of neutral hydrogen, which makes sense. The more neutral hydrogen there is, the easier it is to absorb the CMB photons. And so the optical depth obviously should be proportional to NH1. And then the way that you should think about it is that there is a decay, there is a narrow resonance, and the photons that are coming in will come in at just above 21 plus 1 plus delta. And then when it comes out at 21 at 1 minus delta. And so the total amount of time spent within A21, right, will also determine the optical depth. Okay? And so if I look at how quickly the frequency of the photon is changing as a function of time, you can convince yourself that this is just going to be given by h times omega, because h tells you the expansion rate, right? And so the amount of time spent in the line is just given by something like A21 times delta t over delta omega, which is given by A21 over h E21. Okay, and so that explains this A21 h E21. Okay, and the last thing is this 1 over Ts, which is a little bit more difficult to explain, but let's think about the limit at which Ts goes to infinity. So when Ts goes to infinity, it means that the hydrogen system is very hot. And so there is essentially a democratic distribution between all of the states. And at that point, when Ts is infinite, right, it's already at the maximum temperature in some sense. It's just not going to be able to absorb any more energy. And so you expect the optical depth to shut off as Ts goes to infinity. Okay, so heuristically, this is what the optical depth is, and then I can write down numerically what is it. It's given by something like that, okay? And then there's a bunch of dependencies on like omega b and omega m, which I'm not writing down. Okay, so the optical depth is always very small. It's just something like 1%. So you're going to see that only, roughly 1% times this difference, this ratio here, which you hope to be big, can end up getting absorbed. Okay, so you're not looking for a 2 Kelvin absorption signal, but you're looking maybe more like millikelvin, tens of millikelvins. Okay, so that's the optical depth. And then for the other term, I can use something called detailed balance, which just says that if everything is in thermal equilibrium, then there shouldn't be any effect here. The absorption and the stimulated emission should be exactly cancelled by spontaneous emission. And so this S of Z here, the only thing it knows about is TS, right? Because spontaneous emission is just emission from the atom itself. It doesn't care about the CMB bath. And so if I set T gamma to TS, in other words, if the photon temperature is the same as the spin temperature, then those two systems are in equilibrium and I don't expect any net change. And so from detailed balance, set T gamma equals TS. This should give TB equals 0, and therefore S of Z is equal to TS 1 minus e to the minus tau of Z. Okay? So at the end of the day, the signal that you're after, which is the 21 cm brightness temperature, is TB is equal to TS minus T gamma over 1 plus Z, 1 minus e to the minus tau of Z. Okay? And this is the thing that you're trying to measure. All right? So you will only see a signal when TS is different from the photon temperature. So in other words, when our hydrogen system is not fully coupled and thermalized with the CMB. And in addition, you need some finite optical depth. Okay? So that's two things that you need to see a signal. Any questions at this point? Okay, so maybe that was a bit too much detail, but let me kind of finish up by going to the last thing that we need, which is the spin temperature, and then telling you a little bit about how the spin temperature should evolve and the brightness temperature should evolve as a function of Z. And then telling you a little bit about how do we do the measurement. Okay, so in order to get the brightness temperature, we've already sorted out tau of Z, which is the optical depth. The optical depth, in the optical depth expression, the only thing that we need is TS, which is the spin temperature. And so now I'm going to talk about the spin temperature. And like I said, the right way to think about the 21 cm system is as something that's coupled to a bunch of reservoirs. One reservoir I've already seen is the CMB, which is at T gamma. And there are two others. So one, so TS, what sets TS? Number one is CMB photons causing transitions, which drives TS towards T gamma. Then it is also coupled directly to baryons with temperature Tk My apologies for changing notation, but now the baryons are at temperature Tk. So how are they coupled? Well, when two hydrogen atoms collide, it doesn't have to be hydrogen atoms, it can be hydrogen electron as well. But when two baryons collide and one of them is a neutral hydrogen, they bump into each other, and there's a cross-section for which the collision causes the hydrogen to go from the ground state to the excited state. And that's collisional excitations. And if this is efficient, then it drives Ts towards Tk. Okay? Good. And now there's a last one, which is maybe the most surprising, which is Lyman alpha photons. Through something called the Wouterson field effect. Okay, so there's Lyman alpha photons. We call Tc, the color temperature of the Lyman alpha photons. Okay, so how does this work? Well, suppose you have Lyman alpha photons present in this hydrogen gas, then it can go from, this is the two-level state, it can go up to n equals 2 from the excited state, and then back down to the ground state. Okay, so the presence of Lyman alpha photons allows transitions between 1 and 2. And so it also acts as a kind of thermal bath that kind of, pulls Ts to Tc. Okay? No, but Lyman alpha itself also scatters very well with baryons, right? The cross-section at which it scatters with neutral hydrogen and excites it from n equals 1 to n equals 2 is very, very high. And so it turns out that Tc is usually roughly around Tk anyway. Okay? So now let me just draw this diagram again. And now I'm going to also include reionization because 21cm can be used to look past reionization. We have the CMB. And then we have baryons. And then there's a turnaround in baryons because initially it's just adiabatically cooling and so on. But then at some point you get star formation, right? And so you start getting heating from stars. Okay, so I've drawn here T gamma and then Tk. Okay, and then as I said, Ts is either drawn towards T gamma or it's drawn towards Tk. Okay, and so the typical evolution for Tk is that initially everybody is in equilibrium, and so I'm talking about Ts tracks the CMB, so this is Ts. Okay, at some point it follows the baryons for a little bit because the photons because collisional excitation is actually important for a while, and then as the universe dilutes away the baryons, it kind of turns around and goes back up to the CMB for a little bit. And then when the stars turn on, Lyman alpha is an extremely efficient way in which you couple Ts to Tk. And so once the stars turn on, it very quickly couples to baryons. Okay, and then later, subsequently, it kind of follows the baryons. Okay, so this is the typical kind of lambda CDM evolution of TS. If I draw this as T21, uh, if I draw this as T21 as a function of Z, okay, or equivalently, you can think of this also as a function of frequency. Oh, sorry, my gosh, TB. I'm sorry, I keep confusing all the notation because it really isn't consistent in the literature. It would initially be, at high Z's, it would be 0. And then at some point, there's a little bit of 0 here. At some point, there's a little bit of coupling to the baryons at very high redshifts. So this is something like 70 or so, which is very hard to observe because this is at 21 cm times 70. So it's very long wavelengths. And then at some point, it stays at 0 for a little bit before it dips down. Down here at about Z of, 17 or so. And then the baryon temperature crosses the CMB, and so that causes it to kind of go up and go positive. And then eventually it goes to 0, and it goes to 0 because of reionization. So when reionization is complete, you have no more neutral hydrogen atoms, and so everything just shuts off to 0. Okay? So like I said, the right way to think about this is that this is some kind of spectral distortion to the CMB, and you want to look for this. Okay? So I have like 3 minutes. I'm going to just tell you very quickly how to do this measurement, and of course what dark matter or dark matter decay does to this. There are 2 ways in which you want to do the measurement, very similar to the CMB, right? So the CMB, you have a spectral measurement, all sky average of the energy spectrum, but then you also have fluctuations, right? So you get an anisotropy power spectrum. For 21 cm as well, you can do 2 things. You can either, one, look at the all sky average of TB, and you should try to look for a signal that looks like this. Okay, and the other thing you can do is you can try to look for fluctuations in TB, which will give you some power spectrum. In the case of 21 cm, it's interesting because if you think about CMB, right, where is CMB coming from? It's coming from the last scattering surface. It's a very thin kind of shell that you're looking at. But for 21 cm, because it's a line, at lower and lower frequencies, you're actually looking at different slices of the universe. And so with 21 cm, you're actually able to get a 3D power spectrum with frequency as the third dimension. Okay, so you can get a 3D power spectrum, which gives you a lot more information in some ways. So these are the 2 different ways in which people are trying to measure the 21 cm signal. The horrible difficulty with all of this is that if you try to understand like what are the backgrounds to the CMB, for example, the CMB sits at 60 gigahertz, and it's like in a nice kind of in-between area where synchrotron is not super crazy, and then free emission is also not super crazy. So your galactic foregrounds aren't like impossible to handle. Here, because you're at 1 gigahertz instead of 60 gigahertz, you're well into the range where synchrotron is very, very bright. And so in order to get this signal, you gotta beat down the synchrotron background that's coming from the galaxy. Okay? So in order to do this measurement, where you're picking up just the pure cosmological signal, you gotta cut out all the synchrotron that's coming from the galaxy, and that's an extremely difficult thing to do. And so the status of the global signal, what we call the global signal measurement, is that in 2018 there was a claimed measurement of this trough here, But then since then, other experiments have kind of ruled out their measurement at the 2 sigma level, let's say. But overall, it's just a very difficult thing to do, especially the global signal. For the power spectrum, it's a little bit easier. And the reason is because if you just look at this behavior here, you expect to see quite a bit of wiggling as a function of frequency, whereas most of your foregrounds are smoother. So as a function of frequency, for example, synchrotron is just a power law. The same is true for point sources and so on. Whereas this one has like wiggles. And so one very straightforward thing you can do is you can cut on K modes. You can cut on K modes that are long in frequency, leaving just the short K modes in frequency. And then that is goes some way towards suppressing foregrounds and leaving just the cosmological signal, but it's still very difficult. So currently for anisotropy, for the power spectrum, we only have upper limits on the power spectrum, but no detection yet. Okay, that's the current status. For the exotic stuff, it's quite easy to see what happens, which is that if you have heating, the baryon temperature doesn't scale as 1 plus z squared. Instead, there's some additional heating due to the exotic energy injection. And so, for example, you could have the baryon temperature kind of turning around at this point, and then that completely changes what this signal will look like. Okay? And so we expect, and also for anisotropy, you can do the same thing for anisotropy. We expect that these kinds of measurements will be able to constrain. I hope I didn't remove it, but I said earlier that something like a lifetime of 10 to the 28 seconds is possible. We find that after kind of marginalizing over astrophysical uncertainties, you can probably get something like 10 to the 27, which is still pretty good. Okay, that's just a quick version of it. All right. I think that's all I have to say. Thank you. Yeah. 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 So this TC is basically proportional to the intensity of Lyman alpha. So you can think of like the Lyman alpha spectrum. You can imagine, like, you can ask, like, what is the thermodynamic temperature at which I would get this intensity? That's TC. And what it does is, like when you inject these Lyman alpha photons, you get a lot of transitions between ground state and excited. It enables transitions between ground state and excited state. So if you let this happen for long enough, then the temperature Ts will just get driven to Tc, just like in the CMB. But then it turns out that because Lyman alpha scatters so rapidly with baryons anyway, that these two reservoirs are actually also in very strong thermal contact. And so they end up at the same temperature, which is Tk. And so actually there are only two temperatures that you need to worry about, which is two first order, is T gamma and Tk. Yeah, I hope that makes sense. Yeah. Yeah. No, it would just change Tk. So if you have exotic energy injection, instead of doing the 1 plus z squared, it could turn around, for example. This, like you can get very large changes in the temperature and it's still not constrained because we don't have measurements here. And really the current limits are just not that strong. And so what's going to happen is you'll see that, instead of Ts falling and coupling here, it will couple here instead. And so up here, you could, it would be much shallower, or it could even go into emission. Yeah, so this will be, if you see emission, that's a huge signal that you have exotic heating. Yeah. 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 Uh-huh. Okay. Okay, maybe we should look at it. Okay. Cool. Yeah, thank you.